Lecture 6, Global State and Snapshot Recording Algorithms. Preface, recap of previous lecture. In previous lecture, we have discussed about the models of distributed computation, causality and general framework of logical clocks, that is scalar, vector and matrix clock in distributed systems, and how the virtual time and physical clock synchronization can be used as a paradigm for organizing and synchronizing distributed systems. Content of this lecture. In this lecture, we will discuss further details about the global states, that is consistent and inconsistent states, cuts in a space-time diagram, models of communication in distributed systems, and snapshot algorithm, that is given by the Chandy-Lamport algorithm to record the global snapshot. Global state introduction. Recording the global state of a distributed system on the fly is an important paradigm. The lack of global shared memory and the lack of global clock and unpredictable message delays in an distributed system makes this problem non-trivial. This lecture first defines consistent global state and discusses issues to be addressed to compute consistent distributed snapshot. Then the algorithm to determine on the fly such snapshot is presented in this part of the lecture. System model, which we are going to consider in this algorithm design. The system consists of a collection of n processes P1 to Pn that are connected by a communication channel. There are no globally shared memory and there is no physical global clock, and the processes communicate by passing messages through the communication channel. So the communication channel is modeled by Cij, that is the channel which connects from process I to process J, and its state, that is the channel's state, is represented by Scij. The actions performed by processes are modeled as three different type of events: the internal events, the message send event and the message receive events. So all the processes are basically three events types, that is internal events, message send event and the message receive events. For a message Mij that is sent by a process I to process J, let send Mij and receive Mij denote the send and receive events. So with these notations we are going to see some more details. So at any instant the state of a process I is denoted by LSI is the result of the sequence of all the events executed by Pi till that time. For an event E and a process state LSI, event is in LSI if and only belongs to the sequence of events that have taken process Pi to state LSI. For an event E and a process state LSI, E is not in LSI if and only does not belong to the sequence of events that have taken process Pi to LS state. For a channel Cij, the following set of messages can be defined based on the local states of a process Pi and process Pj. Transit. So transit between LSI and LSJ, that is the local state of I and local state of J, is nothing but the message Mij. That means the send of Mij is in local state of I and receive Mij is not in local state of J. Where it is, the message is in transit, that is in the channel. So, consistent global state definition. The global state of a distributed system is a collection of local state of the processes and the state of channels. Notationally, global state GS is defined as the union of I's, the union of all processes local state, and the union of all Ij, that means all the state of channels. So that means global state is nothing but the collection of all the local states and collection of all the channel states. So a global state GS is a consistent global state if and only if satisfies the following two conditions, that is the condition C1 and the condition C2. Condition C1 says that send Mij is an event is in LSI, that is local state of process I. This implies that the message Mij is either in channel state of Ij or the message is received Mij at the process J's local state, that is LSJ. Similarly, the condition C2 says that if this send event, send of a message Mij is not in the local state of I, this implies that the message Mij is not in the state of a channel recorded, and also the received of Mij message is not in the local state. So we have seen the global state definitions. So global state of a distributed system execution we can see in figure 6.2, which is given ahead. Before that, we have to see that the global state GS1 consisting of a local states LS1 of 1, LS2 of 3, LS3 of 3, LS4 of 2. Let me explain you what does this means. So LS1 of 1 indicates that all the event E1 up to 1 that has been covered in LS1. So in general we have to say that LSI of X is nothing but set of all the events of I which has executed or progressed up to Xth event. So this particular notation is basically referenced over here. So this set of global state GS1, which comprises of all these set of local state, is inconsistent because here the state of P2 has recorded the receipt of a message M12, however the state of the P1 has not recorded its send of a message. So let us see this in the diagram. So in the red, GS1 is shown as inconsistent. So LS1 of 1 will start over here, LS2 of 3, that means will go like this, and LS3 of 3 will come over here, and LS2 of 4 will basically come over here. So you can see that this particular message M12 is causing this particular global state as inconsistent. Why? Because in this global state 1 GS1 it is called the receipt of a message is recorded but send of a message is not recorded. So it's an inconsistent global state example. On contrary, the global state GS2 consisting of local states is consistent. All the channels are empty here except C21 that contains M21 that we will see once we come to that figure. Now global state of a distributed system. A global state GS is nothing but a union of all local states and union of all channel states. This is transitless if and only if the state of the channel all the state of channels are empty, that means no message is in transit. So that global state is called transitless. Thus all channels are recorded as empty in the transitless global state. A global state is strongly consistent if it is transitless as well as the consistent, which definition we have seen. Note that in figure 6.2, the global state of a local states, this is strongly consistent. Let us see in this example. So GS2 comprises of LS12, LS12 is here, and LS24 will come over here, LS34 will come over here, and LS24 will again come over here. So this is GS2, global state 2. This is a consistent global state. Why? Because there is a message which is crossing this particular global state. That means the message whose send is recorded but received is not recorded. So this is an example, or this is under the definition of a consistent global state. Strongly consistent global state, LS1 of 2 will be here, LS2 of 3 will be here, then LS3 of 4 will be here, then LS2 of 4 will be here. So this particular example does not see any message which is crossing this particular line or a global state. Hence, all the channels, when this global state GS3 is recorded, they are transitless. That means the state of channels, they are all empty, and it is a consistent also. Why? Because there is no message which is crossing. Hence it is called a strongly consistent global state. So recording the global state of a distributed system is an important paradigm when one is interested in analyzing, monitoring, testing, verifying properties of a distributed applications and algorithms. The design of efficient methods for recording the global state of a distributed system is an important problem. Now, cuts of a distributed system. In a space-time diagram of a distributed computation, zigzag line joining an arbitrary point on each process line is termed as a cut in a distributed system. Such a line slices the space-time diagram, and thus the set of events in a distributed system is basically partitioned into the past events and into the future events. Past event contains all the events to the left of the cut, and future event contains all the events to the right of the cut. For a cut C, let past C and future C denote the set of events in the past and future of C respectively. So every cut corresponds to a global state, and every global state can be graphically represented as a cut in a computation's space-time diagram. Cut in a space-time diagram provides a powerful graphical aid in representing and reasoning about the global state of a computation. So this is an example of the cut in a distributed system. So this cut basically is a strongly consistent cut. Why? Because there is no message crossing it, and all the channels are transitless. It's a consistent and a transitless. It's called strongly consistent. Consistent cut, where the message whose send is recorded within the cut, but the receipt is not recorded, is called consistent cut. Inconsistent cut says that the future event is crossing into the past event, and this is not correct as far as the distributed system is concerned. That is why this cut is called inconsistent cut. So whenever there is a cut, on the left side will become the past event, and on the right side becomes the future event. So space-time diagram, the cut divides into two parts: the set of events which are happening in the past and set of events which are happening in the future. And this is an important to the reasoning of a distributed system. So these examples are self-explanatory now after so much of discussions. So this is an inconsistent cut. Why? Because a future event is crossing to the past event. Similarly, this event, this is a consistent cut. Why? Because only the past event is crossing the future event. Hence, this is a consistent global state defined by this particular cut. This is inconsistent global state, which is defined by this cut C1. Explanation of the cut in a distributed system. In a consistent cut, every message received in the past of the cut was sent in the past of that cut. That I have already explained. So all the messages that cross the cut from past to the future are in transit in the corresponding consistent global state. A cut is inconsistent if a message crossing the cut from future to the past. Issues in a global state, in a recording of a global state. The following two issues need to be addressed. Issue number 1, that is I1, how to distinguish between the messages to be recorded in a snapshot from those not to be recorded. So any message that is sent by a process before recording its snapshot must be recorded in a global snapshot, and this is the condition number 1. Any message that is sent by a process after recording its snapshot must not be recorded in a global snapshot, and this is the condition number 2 of the issue number 1. Now issue number 2 says that how to determine the instant when a process takes its snapshot. A process Pj must record its snapshot before processing a message Mij that was sent by a process I after recording its snapshot. So now we are going to see an example of a money transfer, and this will give the motivation why the global state recording is not trivial. Let S1 and S2 be the two distinct sites of a distributed system which maintains a bank account AB respectively. A site refers to a process in this example. Let the communication channel from site 1 to site 2, from site 2 to site 1 is denoted by C12 and C21 respectively. Consider the following sequence of actions which are also illustrated in the figure 6.3. Time T0, initially the account of A was 600 and account of B was 200. C12 channel was 0, empty, and C21 was also empty. In time T1, S1 initiates the transfer of 50 from account A to account B. Account A is decremented by 50 to 550, and the request for 50 credit to the account B is sent on channel C12 to C to site S2. Account A 550 and account B 200, C12 50 and C21 is 0. So let us see this complete scenario of transaction between site S1 and S2 in this particular figure 6.3, that is money transfer example. So here you can see that at time T0, site S1 having A, account of A is having 600. At that time, after time T0, it has sent a request to transfer 50 from A to B. Just after sending this request, the amount of A will be decremented afterwards sending this request, and this request will reach here after T2 time at this point instant. Now at this point T2 time, after T2 time, the scenario will be like this. At the S2, now you can see that site before time T3, site S1's transfer of the message was received and it was being updated. Now as time T2, site S2 receives the message to transfer 50 to credit this particular account. So now we can see here, if let us say that the local state of A is recorded at time T0 and it shows that A is 600, and then the local state of B is recorded and that shows that B is having 120 and the channel state is C12 is 50 and C21 is 80. So this, if you sum all the money, this will become how much? 850. That means 50 extra. So 50 extra will appear in the system. So you can see here, the initially both are having A plus B is equal to 800 to begin with, but this particular message to transfer 50 from A to B is in the transit. So the global state, this is recorded, and then at time T2 this is recorded. This is recorded in the sense 120 is basically the amount of B and 50 and 80. So if you sum them, it will become 850. That means 50 will be coming extra. So this kind of recording without any coordination is inconsistent. The reason of inconsistency is that account A's state was recorded before 50 transfer to B using channel C12 was initiated, whereas channel C12's state was recorded after $50 was initiated. This simple example shows that recording a consistent global state of a distributed system is not trivial. Recording activities of individual components must be coordinated appropriately. That means it requires a particular coordination of time and the model of communication. So model of communication is very much going to affect the design of the global snapshot recording algorithm. So that is why we are again stressing upon, or we are looking back again the same model of communication. Recall that there are three different model of communication in a distributed system which is assumed. The first one is called FIFO, the other one is called non-FIFO, and causal order CO. In a FIFO model, each channel acts as first in first out message queue, and thus the message ordering is preserved by the channel. In non-FIFO model, the channel acts like a set in which the sender process adds a message and receiver process removes message from it in a random order. The causal order model, the system supports causal delivery of the message, satisfies the following property: for any two messages Mij and Mkj which are going to the same destination, if send of Mij and if proceeds send of Mkj, that means both the sends, both the message, they have the causal relation. In the send message, then this particular relation will be respected when they are being delivered. That is, receipt of Mij is also going to proceed before receipt of Mkj, then it is called causal order model. of communication. Now we are going to see a snapshot algorithm which basically uses the FIFO channel. So let me tell you that this is an assumption. So this same algorithm for other two models, that is non-FIFO and causal order, will not work. So it will assume that the model is FIFO. So non-FIFO it will not work. So Chandy-Lamport algorithm. Chandy-Lamport's algorithm uses a control message which is called a marker, whose role in FIFO system is to separate the messages in the channel. So after a site has recorded its snapshot, it sends a marker along all of its outgoing channels before sending out any more message. A marker separates the message in the communication channel into those to be included in the snapshot from those not to be recorded in the snapshot. As far as if you see the issue I1 and issue I2, which we have seen earlier about global snapshot. So the process must record its snapshot no later when it receives a marker on its communication channel, and this is the issue number 2. So the algorithm can be initiated by any process by executing the marker sending rule, by which it records its local state and sends a marker to on each outgoing channel. A process executes marker receiving rule on receiving the marker. If a process has not yet recorded its local state, it records its state on the channel on which the marker is received as empty and executes the marker sending rule to record its local state. The algorithm terminates after each process has received a marker on all its incoming channels. So all the local snapshot gets disseminated to all other processes, and all the processes can determine the local state. Let us see the algorithm in more detail. The marker sending rule for a process I has 2 steps. Process I records its state for each outgoing channel C on which a marker has not been sent. I sends the marker along C before I sends further messages along C. Marker receiving rule for a process J. On receiving a marker along channel C, if J has not recorded its state, then record the state of C as empty, follow the marker sending rule, else record the state of C as a set of messages received along C after J's state was recorded and before J received the marker along the C. So the Chandy-Lamport's algorithm has 2 different rules: marker sending rule for a process I and marker receiving rule for process J. Marker sending rule will initiate the process I to record its state, and it will also send the marker on each outgoing channel. Similarly, marker receiving rule for a process J has 2 conditions: on receiving the marker along the channel C, and if J has not recorded, then it will record the state of a channel and also will record its state of a process according to the marker sending rule. If process J has already recorded, then it will record the state of a channel C as the set of messages received along C after J's state was recorded and before J received the marker along C. So first we have to go and see the correctness and complexity of this algorithm, and then we will explain you through an example. So correctness, due to the FIFO property of the channel, this is very important that it assumes a FIFO property of a communication channel. It follows that no message sent after the marker on that channel is recorded in the channel state. Thus condition C2 is satisfied. When a process Pj receives a message Mij that precedes the marker on the channel Cij, it acts as follows. If the process J has not taken its snapshot yet, then it includes Mij in its recorded snapshot. Otherwise, it records Mij in the state of a channel Cij. Thus condition C1 satisfies. So this is according to the marker receiving rule, and this is basically the marker sending rule. So this shows the correctness of the snapshot recording, and which is a consistent global snapshot or global state which is recorded by this algorithm. The complexity, the recording part of a single instance of an algorithm requires of the order E messages, where E is the number of edges, and the time complexity is of the order D, where D is the diameter of the network. Now let us see the properties of the recorded global state. The recorded global state may not correspond to any of the global state that occur during computations. So consider two possible execution of a snapshot algorithm, which is shown in the next figure for the previous money transfer. So here in this particular example, we will see two different cases of the marker or the snapshot initiation, which is shown by the circle in the first one, and the square is another initiation of the same global snapshot recording algorithm, which is shown by the red dots. The first snapshot shows the green dots. We will see that in both the cases it will record a consistent global state in that same previous example. So first we will see this example, this particular example we will see first, and this we will see next. So site S1 initiates the algorithm just after T1. Site S1 records its state as 550 over here. This is site S1 records and sends a marker to the site S2. The marker is received by the site S2 after T4. When site S2 receives the marker, it records its local state, that is because it is receiving the marker for the first time. So in the marker receiving rule, the first condition will be satisfied, so it will record its state as 170, and the state of a channel C12 will be empty in that case, and then it will send the marker sending rule along the channel C1. Now when state S1 receives this marker, which is sent by site S2, it records the state of a channel C21 as 80. Why? Because it has already recorded its state, so it will go for the second option in the marker receiving rule. So only the state of a channel is recorded, and which is shown as 80. So if you sum them, it will be 800, and that is the money which the system has begun. So hence the 800 amount in the system is conserved in a recorded global state by this particular algorithm. In second example, and this is shown over here that I have explained. So here the global state will be recorded, that is A will be recording 550 over here by site S1 before sending the marker sending rule, and when the marker is received, so it will initiate, site S2 will initiate the marker receiving rule. So it is recording for the first time, so it will be recorded the state of B as 170 after time T4. Now then it will also record its state of channel C12 as 0, and then it will send the marker to the site S1. Site S1 on receiving this particular marker will initiate the marker receiving rule. The second condition, because it has already recorded its snapshot, or it has already recorded its state, so now it will only record the state of this particular channel, and that is nothing but C21 is basically having the $80. This particular portion will be captured over here. So if you sum them, it will become 800, that is nothing but the start condition of the system. Hence the system basically records correctly the consistent global state. Another example we are going to see wherein the markers are shown in the green dotted arrows. In this example, I will explain you the working of a Chandy-Lamport algorithm. Now here you can see that before sending the message, the channel state is recorded at S1. So marker sending rule will record its channel, will records its state, and then it will send the marker sending rule. Marker will be sent on the outgoing channel, that is C12. Now when the marker is received by state 2, then it will record its state. S2 has not yet recorded its state, so S2 is going to record its state as 120. So 120 is the current value of S2 of B, and it will also record its channel as C12 as empty, and then it will send the marker again back to 1. The marker will be received by site S1 at this end. Since it has already recorded its state, so it will only record the channel state of 2-1. What it will record in the channel state? So it will record the channel state as this amount, that is 80. Now if you sum them, it will become 800, and this is a consistent global state which is recorded by this particular algorithm, and the two examples have clearly shown this particular thing. Now properties of the recorded global state: in both these possible runs of the algorithm, the recorded global state never occurred in the execution, that is in the distributed execution. This happens because the process can change its state asynchronously before markers it sent are received by the other sites, and the other sites record their states. In the sense, due to the asynchrony of the sender and the receiver processes, so the snapshot which is recorded over here may not coincide with the distributed execution which is taking place, but the system could have passed through the recorded global state in some equivalent executions. The recorded global state is valid state in an equivalent execution, and if the stable property, that is a property that persists, holds in the system before a snapshot algorithm begins, it holds in the recorded global snapshot. Therefore the recorded global state is useful in detecting the stable properties of a distributed system. Now we are going to see the variants of a global snapshot algorithms which are available. We have seen these global snapshot algorithms, as I told you, that they are very sensitive to the communication channel model, and the global snapshot algorithm given by Chandy-Lamport basically uses FIFO model of the channel. So here it is also already written that the Chandy-Lamport algorithm requires the channel model to be the FIFO model. The Chandy-Lamport algorithm uses the order E messages to record the snapshot and uses order T time. Now Spaghetti and Kerens, they have improved this algorithm which supports the concurrent initiation, so that is already following the FIFO model. Now then there are algorithms which uses non-FIFO model, and to use the non-FIFO model, it is not trivial, it is very, very difficult to design the snapshot algorithm in a non-FIFO model. So Liang, Li et al. And Maton, there are three different algorithms are basically discussed in the literature. Now these algorithms basically require the concept which will either delay the message sending of the further messages till the messages which is sent by the particular process is received by the receiver. So this delaying can be basically acknowledged using the acknowledged message, or using the piggyback message can be used to synchronize or to know whether the messages which are sent is being delivered at the other end or not, because it's a FIFO model. It cannot assume that the messages which are sent are being delivered. So basically there are various implementation, various algorithms uses various techniques. Some are using the acknowledgements, so delay, and once the acknowledgement comes or the acknowledgement is being piggybacked to deal with the asynchrony of the communication channels. Then we will see some algorithms which uses the causal order, that is CO model. Causal order is a basically proper subset of FIFO model. So if you assume a causal order, it will be even simpler than the algorithms which you have seen in the Chandy-Lamport. That means the algorithms need not have to send the markers on all the outgoing channels, so require the causal delivery support. So channel message contents need not to be known, and hence this particular model, if it is assumed, then the global snapshot algorithm will become quite even simpler or easy. So these are different variants. If the variations are in the form of the communication model, so we have already covered that. That means how the Chandy-Lamport algorithm will be basically, or improvements of these algorithms which we have seen. Conclusion: recording global state of a distributed system is an important paradigm in the design of distributed system, and the design of efficient methods of recording global state is an important issue. This lecture first discussed the formal definition of a global state of a distributed system, and then basically we have discussed the Chandy-Lamport algorithm to record the snapshot of a distributed system. In upcoming lectures, we will discuss about the distributed mutual exclusion algorithms. Thank you.